Hi guys, we're back to talk about our last topic, which is energy. So in our textbook, this topic is covered in chapter 13, and we're really going to go through all the sections of that chapter, but we're going to break it up into 3 videos. So this one will be about fossil fuels and their use for energy production, and then also just kind of some introductory energy stuff. Then the second video will be about nuclear energy, and the final video will be about different renewables. So that's what to expect. And let me share my screen so we can get started here. Fossil fuels. All right. Let me start slideshow from the beginning. Okay. So we talked about energy earlier on in the semester when we started to just think about what energy is. And you may remember that energy is a concept, and it is it's something that has the ability to do work. So it's often contained by matter, but it's not matter itself. It's just something that has the ability to do work. So work, then what's that? That doesn't necessarily mean that you're like a contractor or a nurse. Work in the physical or energy sense means the application of a force over a distance. So you're pushing or pulling something through space. And then remember, we said that could be like water pushing on other water molecules around it, or on a rock or a piece of sediment, or that could be energy between different kinds of cells, or energy between different kinds of atoms that are pushing or pulling on each other. And then when it comes to, I guess, all energy, but kind of energy that we use in our society, we have certain kinds of metrics that we use to measure it. So you might remember that joules is the kind of SI unit, or scientific standard unit, that's used to measure energy. And there's other units as well that you may have heard of, or you might even be more familiar with. So calories in particular are a unit that we're used to hearing about. And some people are not exactly familiar that calories are actually a unit of energy. And that's how we report how much energy is contained in our food. 1 calorie equals 4.2 joules. And then actually the energy that's reported on our food, as an aside, is actually a kilocalorie, so 1,000 calories. And then BTUs are another unit of energy. Sometimes you might hear these in reference to like firewood or fires. So a BTU is a bigger unit of energy, 252 calories. So I don't need you to remember those exact numbers, but just so you understand, those are ways that we can measure the amount of energy that is being used to do something, or that is contained by some sort of material that then may be able to do work in the future. So on the other hand, we also think a lot about power, right? How do we power our economy and power our homes and power our refrigerators? And so power is the rate of energy flow or work that can be completed. So instead of just saying the amount of energy, it's saying the amount of energy used over a given time, right? Because if your refrigerator's on for a minute or a year, it's going to require a different amount of total energy, but it would still have the same amount of power that's required throughout the time that it's going to be on. So anyway, that's the difference between power and energy. So you're probably familiar with watts, because when you buy a light bulb, it will tell you about if it's a 60-watt bulb or a 100-watt bulb. And so a watt is a measure of how much power is required to run a particular appliance, whether that's like a refrigerator or a light bulb. And it is 1 joule per second. That's what a watt is. So your light bulb, if it's a 60-watt bulb, is using 1 joule of energy per second that it's plugged in. And then one final unit that we'll refer back to that you may have come in contact or heard about before is called a kilowatt hour. And a kilowatt hour is basically an amount of energy that is used by something that requires 1,000 watts for a period of 1 hour. So pulling 1,000 joules per second times 1,000. So actually, I guess that's 1,000,000 joules per second per hour. No, I guess it's 1,000 joules per second for an hour. Anyway, the point is that it's an amount of energy that would be used by that over time. Okay, so just to compare, the average US home uses almost 11,000 kilowatt hours each year. Okay, so throughout the course of the year, 365 days, you're using a certain number of kilowatt hours each day that add up at the end of the year to 11,000 kilowatt hours of energy have flown through your home. The Rock Creek Power Dam, which is something that you may have seen driving up the Feather River Canyon, produces 1.2 billion kilowatt hours per year. So that's going to be able to fuel a lot of homes. And then a solar panel can produce 200 watts, so about 200 joules per second. So yeah, anyway, that's a little bit of a reference. So obviously something like a power dam has a much greater ability to produce power than a single solar panel. We would need a lot of solar panels to do the same work that a hydropower dam can do. Okay, so that's just some energy basics, but the main kind of topic for this video is about fossil fuels. So a fossil fuel is something like coal or something like petroleum products, like the gasoline that we put in our car, or natural gas. And they're all considered fossil fuels because they're fuels that we dig up from the ground. And basically, these are all just really ancient organic compounds that originally came from plants and animals. And animals, we learned earlier in the semester, get their energy from plants. So all originally from plants. And these plants photosynthesized in the world 300 to 400 million years ago during a particular time in geologic history called the Carboniferous era, that had a particular climate and a particular kind of evolutionary situation where there was a big kind of boom of organic matter on the continent or on the planet. And these organisms captured energy from the sun, they photosynthesized, and they made different kinds of sugars and other organic compounds, and then some larger kind of plankton in the ocean may have eaten some of these plants. And then on land, some of these plants got kind of buried in swamps where there wasn't a lot of contact between oxygen in the air and the plant matter that was being buried. And over time, that organic matter that was kind of disconnected from oxygen that would have allowed bacteria to successfully break it down, combined with kind of pressure of overlying soil buildup and heat from being inside the earth, kind of transformed that plant material into coal, kind of going through a process where it looked a little bit like peat, and then another material that's kind of in between peat and coal called lignite on the way. So coal contains all these organic molecules that were originally part of plants. On the other hand, petroleum and natural gas were primarily formed in the ocean. And in this case, it's little plankton, these tiny little critters that swim around in the ocean, and they were similarly kind of buried on the ocean floor underneath layers of different kinds of sediment. And they have been pressurized and heated by contact with the earth, disconnected from oxygen as well, and they have turned into oil and gas deposits. And so now we realized in the last few hundred years that we could dig up these old organic molecules and we could burn them to release energy, just like we can burn new organic molecules like wood to release energy as well. And in particular, these organic molecules have a much higher concentration of organic molecules kind of packed together in a small space. So when we burn them, we can release more energy than we can by burning things like wood that might exist on the surface. And then, of course, there are some other kind of undesirable outcomes that are resulted from that. But it certainly has given us an enormous capacity to use energy and to transform our environment in a way that is really unprecedented in human history. So just to kind of think real scientifically about this, I have 3 different images here, I guess 4 different images here, showing on the top left natural gas, which is this kind of small, very simple compound. Natural gas is primarily made of methane, which is carbon surrounded by 4 hydrogens. Then gasoline is a kind of long carbon hydrogen chain. Okay. And then coal, a picture of this, what this chemical compound would look like on the top right, is a very complex solid. So again, or just to review, natural gas is actually a gas. These small molecules are able to easily move around in the atmosphere, whereas the chains are a little heavier. They form liquids near the Earth's surface. Coal is a solid, and it is this kind of bulkier compound. And also, it tends to have more things besides just carbon and hydrogen in it. And so when we burn coal, we tend to get a lot more kind of contamination from impurities in the atmosphere rather than when we burn gasoline and natural gas, although there can be impurities in those other forms of energy as well. So basically what we do with these things once we dig them up is we burn them. So we heat them up, we expose them to oxygen, and they release energy, and they turn into carbon dioxide, they turn into water, and then they, depending on what kinds of impurities are in the compounds, they might also release like sulfur dioxide or NOx gases, or hopefully not, but often things like maybe even mercury into the atmosphere. So we capture that energy that's released, and that's what we're using to fuel our cars, to make electricity, and use all the energy that we do in our life. Okay, so we went over that, so I'm going to skip that slide. You can go back and read it in the PowerPoint slides if you want. Okay, so what is the problem with using fossil fuels? In some ways, as we mentioned, this is kind of a great innovation that allows us to have a lot more energy and get a lot more work done than we ever were before. It's a really powerful tool. So that's all true, but unfortunately, there are some really unfortunate side effects. So the first one is that they are not unlimited. And they are not renewable. They have been formed from organisms that lived on this planet in very specific conditions over 300 million years ago. So as we use them, we're not able to kind of remake more. And so we're using them, and eventually we're going to use them up. And so we need to have a plan to be able to transition off our dependence on these kinds of fuels, because eventually they're not going to be here anymore, and we need to have a transition plan. So that's number one. A second component is that extracting these fossil fuels from the ground, from these locations where they have been buried deeply for hundreds of millions of years, is often quite environmentally damaging. So certainly locally in the area where we have these big mines or big wells, we can create really significant impacts, but even kind of downstream or regional impacts can be felt as well. So we'll kind of go through and look at some examples from each of the 3 fossil fuel types in a few minutes here, but that's an issue. Then we're increasingly becoming aware of the negative impacts of the release of the greenhouse gases that come about when we burn these fossil fuels. So in the last slide, I showed you that when we take these carbon hydrogen compounds and we introduce oxygen and introduce some heat, we are able to combust them and transform them into carbon dioxide, and that is a greenhouse gas. And we know that the carbon dioxide is dramatically increasing in the atmosphere. We've talked about this early in the semester, so we won't go into it a lot more here, but this has a lot of negative impacts. So we're increasingly feeling and being hurt by. So that's a definite concern about the dependence on fossil fuels. Then fourth, burning them unfortunately doesn't only release carbon dioxide, but it also releases other kinds of atmospheric pollutants. So we said when these carbon hydrogen chains or coal compounds aren't exclusively just carbon and hydrogen, but have other sulfur or nitrogen or mercury kind of bonded in some of those structures, then when we burn them, those contaminants are released into the atmosphere as well. So we talked about atmospheric pollution as well, and a lot of that is associated with burning of these fossil fuel types. And then finally, we have to deal with different kinds of toxic byproducts that might be associated with the mining and kind of refining and manufacturing of these fuel types. And so we might have a lot of kind of big waste ponds, and those themselves, kind of aside from the fuels, might be creating local or regional environmental problems. Okay, so regardless of these negative outcomes, at this stage, we're still very dependent on fossil fuels. So this is from the EIA, the Energy Information Agency Administration, which is part of the federal government, and then the Department of Energy. And so this is showing the 2019 statistics, showing that petroleum is responsible for producing 37% of kind of our energy that we use in the United States each year. And petroleum is primarily used in the transportation industry, right? This is the gas that we put in our cars, our trucks, our planes. So that is a lot of energy that we use to do that, and we primarily rely on petroleum to get that done. Then natural gas, the next biggest component, is 32%, so also quite big. This is used for more varied uses. Some in transportation, there's like natural gas buses and things like that, some rail lines, but also to produce electricity. Coal, 11%, is going down compared to where we were even a decade ago. And coal is almost exclusively used to create electricity. Nuclear electric power is about 8%. That's also primarily or almost exclusively to produce electricity. And then renewables, about 11%. That's up a few percentage points from a decade ago. And this is also primarily for electricity production. So renewables include a lot of different types of energy, hydroelectric, like dams that create hydropower, burning wood or biofuels or biomass waste to produce electricity, or some biofuels are used kind of as petroleum additives or petroleum replacements, like a biodiesel type of thing. Wind, 24%, that's electricity producing, solar 9%, and geothermal 2%. So again, we'll talk about renewables more in a future lecture, but the point here is that fossil fuels are still a huge component of our energy system. And if we want to be using a lot less fossil fuels, we need to really expand our capacity to depend on these other energy types. They all have trade-offs, and some may be better at making electricity, some may be better able to create some sort of transportation fuel, but we have a lot of work to do to move away from fossil fuels. Okay, so this is a global picture, right? The last one was a US picture. So this is kind of showing changes through time: nuclear, renewables, natural gas, coal, and then liquids would be like petroleum, gasoline products. And you can see all of them are on the rise. We have more people on the planet, becoming accustomed to a more kind of wealthy way of life, many people, so having access to better indoor electricity and cars, personal family cars, which may not have been true for many families in the past around the world. And so as we do that, we're just ramping up all the different types of energy use. And so again, just to kind of illustrate, we are very, very, very dependent on and very, very accustomed to being able to use a large amount of energy. And so if we want to get away from these liquids, coal, and natural gases, all of which are the three highest fuel type uses globally, we need to be working hard to consider and develop alternatives. Okay, so this is a picture showing different countries' use rather than global use of all fuel types. And you can see that originally the United States was out in front, but China, which has a much, much bigger population than we do, I can't quote off the top of my head, but like maybe at least 4 times as many people as we have in the United States, has taken off. And starting in 2009, China is a bigger energy user than the United States, but the United States is still huge. India and Russia are also big players. And then the EU as a unit is a big player as well. Each individual country in the EU, like Germany or France or Italy independently, is much smaller in terms of population and overall energy use, but kind of as a unit, they are also accustomed to using quite a bit of energy. Okay, so another way to think about this is per capita. So just to review, per capita means per person. So we could think of, how much energy does China use and how much energy does the United States use? But then if we want to think about how much energy does each person in the United States use versus each person in China, that would be a per capita comparison. So this graph is showing a per capita comparison of different countries. And you can see this is a situation where the United States is actually not the worst of the worst, but it's kind of within the top 10 biggest uses per capita. Things like Iceland, Qatar, Kuwait, Norway, Canada are actually higher. Saudi Arabia, Australia, Sweden, South Korea, Russia, Germany. So many of these countries are very cold or very hot. They have a big energy requirement to kind of either cool or warm probably homes and offices, but also just kind of a more developed and a wealthier country where people are used to having access to greater energy, maybe have bigger homes, more electronics in their homes, more cars per family. So that's contributing to this high energy use. And then you can see China is considerably less, even though since they have so many people, they're overall using more energy than us. So yeah, China's back there using about, 75 million BTU per person per year, whereas the United States is more like 300. So we're using like 3 or 4 times the amount of energy per person in our country. And that is equivalent to about 60 barrels of oil per person per year that we're using in the United States. So if you've ever paid attention to energy markets, it's all about barrels, what's the price per barrel, how many barrels are being produced. And so about 60 barrels are required to feed your energy needs. Okay, so just some more graphs because I think graphs are interesting. Unfortunately, this video is kind of cutting off the end a little bit of the per capita graph on the right, but it's actually very, very similar to the graph on the left, which is total US energy consumption. So these are both United States graphs. And again, overall consumption on the left, as opposed to per capita consumption in terms of BTUs, remember British thermal units, shown on the vertical axis through time from kind of the Industrial Revolution period. You can see in the mid late 1800s, this starts to creep up. And then we can start to see some little drop-offs like during the Great Depression in the 1930s on both graphs. And then kind of a little drawdown in the 70s and 80s. And then today we're actually seeing a little bit of drop off, or in the last decade, we've seen a little bit of a drop off. And that has less to do with economic downturns like the Great Depression and more to do with just greater energy efficiency, dependent on technologies, and just kind of improved use of our energy. Of course, in the last couple months, we've also seen a big drop off in energy use. I was reading a report earlier in the week that was saying globally we're down about 8% energy use in the last couple months, which is actually not as much as I might have thought. But that's probably, hopefully, a fairly short-term drop off that will not be lasting for like decades. Okay, more graphs, because I love graphs again. So this is showing same thing, total energy consumption on the left, and then per capita energy consumption on the right. And then you can see, in this case, it's broken down by different energy types. So focusing on the graph on the left first, we can see oil has gone up quite a bit. And again, that's oil, or is kind of synonymous with petroleum, or what we think of as gasoline that we put in our cars. And that has kind of come online more recently than things like coal, which kind of was developed and was the original fuel source of the Industrial Revolution, that we can see kind of came online in the 1800s. And then that is kind of, even that is an earlier fuel source, or sorry, a later fuel source compared to wood, which was incredibly important, especially on a per capita basis, kind of before the Industrial Revolution, to produce energy in people's homes. And then we have some more recent introductions of energy sources like nuclear power, coming up in the 1960s and 70s with those technological advances, and then things like hydroelectric and other renewables just kind of starting to really come online in a significant way in the last decade or so, but still they are used at a much smaller scale compared to the other fuel source types. Okay, what do we use our energy for? Industrial manufacturing and production, so all the manufacturing of our electronics and our, chairs and our clothes and our this and that. And then transportation is also really huge. And then residential and commercial are both smaller than that. So anyway, 4 kind of main sectors. Okay, so with that understanding, I want to kind of move on and then just kind of go through it a little bit more detail, some of the specific impacts associated with the 3 different fossil fuel types. So first of all, we'll start with coal. So remember, coal is kind of the OG, the original fossil fuel type that we started to utilize in Europe in the late 1800s, that kind of set off the Industrial Revolution. And there's a lot more coal out there compared to the other fossil fuel types. Some estimates say that there's 10 times more coal compared to all the oil and gas combined. The US is home to some of the largest reserves of coal. So especially kind of up throughout the kind of Appalachian region of our country, there are underneath the ground buried these 300 and 400 million year old coal reserves. Russia and China also have quite a bit of coal as well. Of course, US, Russia, and China are big countries. They cover a lot of area, but those 3 countries have about 2/3 of all the coal that we know of on our whole planet. So those 3 countries are involved in a lot of the coal mining and production. And coal is cheap. It's cheap compared to the other fossil fuel types and other energy producing types. It's also cheap if we don't consider all the kind of downstream cost, or what economists would call externalities or externalized costs, and the kind of negative impacts of all the atmospheric pollution, et cetera, that's associated with the use of coal. But kind of, on a very basic level, it's just a cheaper thing to buy and use to create electricity compared to the other fossil fuel and energy types. So one of the issues with coal, before we even get to the atmosphere, is that the mining for coal can be pretty destructive, certainly to the environment, and then also kind of famously to the health of people that work in coal mines. So there's kind of two types of mines. There's the kind of classic tunneling coal mines, where people would kind of go down through big shafts and then work underneath the ground to mine coal. So this is kind of like burned into the American memory. Many people have worked in coal mines. Some people still work in coal mines today. And then there's also a lot of what are called surface mines, or sometimes referred to as mountaintop mines. So this picture on the bottom right is a picture of what's a mountaintop mine or a surface mine, which is a lot safer for the people that work in the mine, but is obviously super destructive to the local and regional environment, because they basically just take off all the overlying rock and soil, and then they dig down to where the coal beds are, and then they remove them from the surface. So this is a mine that's called the Horbit 21 mine, and it's a 12,000 acre mine in West Virginia. So you can imagine the local environment and local communities have a really big, certainly like recreational, aesthetic, but also kind of environmental impact from living in the region of this mine. So I think I've already mentioned this before, but just to review, coal is primarily used to make electricity. About 40% of the electricity that's produced worldwide, and about 40% of the energy that's produced in the US comes from coal. And that's, at this point, pretty much the only use for coal. Obviously, electricity is really important. It's used at all levels of industry, manufacturing, retail, commercial, and in people's homes and schools. So it's a really kind of ubiquitous need that we have for our energy, and coal makes up almost half of the resource that we use to produce that. So how do we use coal? How do we get the energy out of coal to produce electricity? There's a video clip that I'm going to post with these other video clips. It's about 4 or 5 minutes, and it's kind of a good illustration. So I'm going to ask you guys to watch that. But just quickly and basically, there's several different kind of like specific details of different methodologies that can be used. But the general plan throughout all of them is that the coal is broken down into small pieces, and then it's burned. And as it's burned in kind of a boiler, which you can see in this diagram at the bottom, the energy that was contained in the coal is being released through this combustion reaction, where we're taking oxygen and some heat, and then burning the carbon compounds in the coal. And that energy is boiling water. The water is evaporating as steam, and it moves up through pipes, and then that steam, as it moves, turns a turbine, which turns a generator. And we're not going to get into all the details of electricity production, but generators typically use magnets to create electrical charges. And then these electrical charges are being able to be transformed kind of kinetically by moving along different kinds of wires that have the capacity to be electrical conductors. And so they move this energy along these power lines into people's homes or into businesses or kind of industrial manufacturing plants. So that's kind of the basic idea of what they're doing with the coal. And again, this video is short, and I think it's instructional, so please do watch that video clip. Okay, so that's kind of an ingenious idea, but we already mentioned some of the downsides are, first of all, just kind of the local impact of the mining, but then as we mentioned, there's also a lot of impact to the atmosphere. So first of all, coal contains less energy kind of per pound or per gram of coal burned compared to the other fossil fuel types. So natural gas has the highest, petroleum has kind of a medium amount, and then coal has the lowest amount of kilojoules, so 1,000 joules that are able to be produced per gram of this material burned. So first of all, we're just not getting as much bang from our buck in terms of how much energy we're getting from the coal. So that's a consideration. And then below, I have a chart that contains data also from the EIA that I mentioned before, the Energy Information Administration. And this is showing CO2, which is obviously a greenhouse gas, carbon monoxide, NOx, sulfur dioxide, and particulates. So these are all atmospheric pollutants that we talked about in the atmospheric pollutant lecture. So I'm not going to go into all the issues associated with them. You can look back to that lecture if you don't remember, but kind of looking at a comparison between natural gas in one column on the left-hand side, then oil, right, which is this kind of liquid petroleum group of products, and then coal, we can see that kind of coal ranks pretty low, in most cases is the worst in terms of how much pollutant is produced per the amount of energy that we're gaining from the production of that product. So in this case, it's pounds of pollutant per billion BTUs produced. So coal has the most carbon dioxide, followed by oil, followed by natural gas. It has by far the most carbon monoxide, followed by natural gas and oil. It has the most NOx produced, although it's a similar amount to oil, and then much less produced by natural gas. SO2 is by far and away produced more by coal than oil, and very little produced by natural gas. And then particulates are actually not quite as much produced by coal compared to oil and natural gas. And that's because the coal, as it's being burnt, is primarily in these kind of contained environments where it's kind of bubbling up into water, and we're capturing the particulates before they're getting into the air, whereas oil or natural gas might be burned like in your car, where we don't really have as good of a capture mechanism. Anyway, so coal is just not as good as a, from a bang for your buck perspective in terms of how much energy it's producing, and then it's undesirable in terms of how much it's pollution it's creating compared to how much energy we can get. So even though it's cheap compared to the other sources up front, we have these downstream costs that we're ultimately paying for in other ways. So that's important to keep in mind as well. Okay, so next fossil fuel is petroleum, which we also sometimes call oil. And then gasoline is the form of this that we're most familiar with. That's what we use when we go to the gas station. Then diesel fuel, maybe you have a truck that runs diesel, or something else that runs diesel. Jet fuel, kerosene, petroleum jelly, like Vaseline, kerosene wax. These are other kind of things that are also petroleum products. So this is a little image here on the right that shows products made from a barrel of crude oil, and this is a little out of date, 2012, but it would be similar today. So gasoline is the biggest, something that we have the biggest demand for, that we make most of, but then there's some other byproducts of gasoline production. And so we get some diesel fuel, some jet fuel, and then some other things like kerosene and petroleum jelly as well. And then like for use in plastic production, things like that, right? Plastics are petroleum products as well. It's good to remember. And then the main use for petroleum is for transportation. We all drive our cars around a lot, and if we don't drive our cars around a lot, other people are driving their cars around a lot and flying around a lot and taking buses around a lot. And all these things are using these petroleum products. And then I just mentioned before, plastics are also petroleum products as well. We also use a lot of plastic. Okay, so there's all these things we could have like a whole class about. how they work and their environmental impacts. But some of the more kind of recent issues with petroleum production is that over time we have kind of used up a lot of the easier to access and cleaner sources of petroleum that were out there. And so we've increasingly moved towards kind of drilling for oil in places that are more dangerous for people to work and produce us kind of lower quality oil in locations that cost more money to extract the products, and then are more vulnerable to different kinds of environmental issues. So one of these, one example of this would be the kind of move to more deep ocean drilling. And so a lot of this happens in places like the Gulf of Mexico or in places like in the Middle East. And you may remember, let's see, this is probably 10 years ago now, but there was this big Deepwater Horizon catastrophe that happened off the Gulf Coast in the United States. And this happened where one of these deep oil drilling stations caught on fire. And so first of all, it's difficult to get out to a deep water ocean drill place and try to kind of handle the problem once it starts. So this is very dangerous for the people that were working in this location. It was very difficult to get this fire out. And then we had oil spilling out into the deep ocean. So it was really difficult for us to go in and put a cap on it. And this actually took us months and had hugely devastating impacts to the marine environment here, to lots of organisms that got coated in oil and ended up dying, but then was also hugely negatively impacting local human communities and local businesses and economies that were kind of dependent on the tourism and recreation around kind of the beaches in this area that were essentially kind of shut down, if not at least very undesirable to spend time in, as they were completely coated in oil. So this would be kind of an example of one of these costs that is not included when we think about, how much does coal cost versus oil cost. We're not considering how much cost is associated with a massive oil spill, and that is ultimately a cost that's paid by society. So something to consider as well. Okay, another example of us kind of becoming increasingly dependent on kind of less desirable forms of petroleum products is our movement in the United States towards the kind of drilling of these tar sands and oil shales. So tar sands are areas of sand and shale, which is kind of like slate that like breaks apart in your hand. It's like a rock product that are basically coated in hydrocarbons and some kind of beds of coal as well. Oil shale is a fine-grained sedimentary rock that it's coated in kerogen, which is another petroleum product. And so basically, instead of drilling, like, putting a well down and then hitting an area where we can pipe up liquid petroleum, we are now going in and extracting sand or rock and then trying to get the oily coating off the rock and try to kind of purify that oily coating by getting all the sand and the rock separated from it, and then being able to use that petroleum product once we've removed it from the sediment. So this is really energy intensive to do. It's also very water intensive to do. We have to use a lot of water to extract the energy product off the sediments and rock. And this is particularly done in places like Alaska and Canada. And this is considered a low grade oil product. So there's low grade output or low energy output compared to the weight of the ultimate product that we get and compared to the amount of carbon dioxide that's released. So it's kind of moving more towards the coal side on those kind of charts that we looked at a few slides back. So not as much bang for your buck. And this is a big tar sands facility that's in Alberta. And so recently we've had a bunch of pipeline controversies in the United States, as there has been an interest by some big, both American and Canadian companies, to build pipelines that go through the United States, particularly in the Midwestern area, to move oil all the way, in some cases from Alaska, but also from Canada down to the Gulf Coast, where a lot of oil is then transported to other parts of the world. And there's a lot of different controversies around the movement of oil, the potential spillage of oil, the kind of autonomy that people have over their private property or environmentally sensitive areas, or kind of culturally or Native American owned or valued areas, and so on and so on. And we're not going to have time to get into all those issues, although they are interesting and important. But just one of the many things that people were kind of protesting when they were interested in when some people were interested in limiting the movement of fuels through their area, is they were kind of protesting against the type of fuel that would be used, that would be moved. They were saying, we don't want to be supporting the extraction of tar sands and oil shales. We think this is ultimately a bad investment that our society is making. We don't want to support this. We think that our energy, not like Jules energy, but our kind of societal and political energy would be better spent in investing in other kinds of energy producing products like renewables. So anyway, thought I would mention that. Okay, so finally, natural gas is basically the cleanest of the fossil fuel types. It's the simplest molecule, which is most likely to be burnt to form exclusively CO2. It's mostly just methane, that carbon with 4 hydrogens that we looked at before. It has the most bang for your buck in terms of how much energy you can get by burning it. It burns the cleanest, so it releases the fewest other atmospheric pollutants, so it has the lowest carbon footprint. However, it's often associated with coal beds, so a lot of times we're mining for natural gas in a similar area, and in some cases, even the same company might be like mining for coal and natural gas at the same time. But the biggest issue or the biggest concern around natural gas is that one of the technologies that has been used to extract natural gas recently is something that's called hydraulic fracturing, that you might have heard referred to as fracking. And basically, to boost the extraction of this material, what companies have figured out is that we can pump water down into the ground, and that water contains a mix of different kinds of chemicals and lubricants that are going to help along with the water pressure, fracture different kinds of maybe shale or maybe even some like coal beds and stuff apart. And then as they break, the gas that's trapped in these little gaps in the earth will be able to kind of seep out of like coal beds or other kind of pervious, like sandy and other surfaces that are down there. And then the natural gas can come up through these pipes into natural gas producing plants. So some of the concerns around this hydraulic fracturing or fracking process is one, that it requires, like the tar sands and oil shale, a lot of water to extract this. So as we're kind of considering how much water we have to go around and what's our best value for water, a lot of people are questioning how much water we're using to extract these certain energy types. Another major concern that some folks have is that the chemicals that are used as along with the water pressure to break apart rocks and lubricate them so that the natural gas can flow more easily are a proprietary secret that's owned by companies. So for the most part, they don't need to disclose them. So they have been approved by the EPA. So there are people that are looking at these things and determining that they're safe. But many people that live in this local environment are concerned about the toxicity and the privacy or the lack of transparency in the way that these different kinds of chemicals are being released into their local and regional environment. And primarily they're concerned that those chemicals and then also just the natural gas itself that's being kind of released from where it may be trapped under the ground is potentially contaminating groundwater. So before we said 50% of Americans and 95% of rural Americans depend on groundwater to kind of fuel their homes. And people that have looked into this have noted extensively that yes, in areas where fracking is taking place, there's much, much more contamination of groundwater relative to other areas. Now, one caveat is that these areas around where fracking is taking place would likely have some amount of natural gas or methane in them already, just because they're in areas where this gas exists underground. So some of the contamination might not be exclusively because of the fracking, but even kind of correcting for that difference, it is a well-documented phenomenon that fracking does lead to contamination of water by methane and by other contaminants. And then finally, an area that is kind of increasingly being documented is that as we're fracking, as we're pumping water and other lubricants underneath the ground, we're increasing the risk of earthquakes in areas where this is happening. And conceptually, this makes sense, right? If you put a lubricant, something that makes things more slippery, along a fault, then that fault is more likely to slip. And so the USGS is still compiling research about this, but it is becoming kind of increasingly a compelling story about the correlation and causation, not just correlation, between hydraulic fracturing and earthquake risk. Okay, so knowing this, what do we do? Well, first of all, the reason that we use all these fossil fuels is because we use a lot of energy and we depend on a lot of energy. So first and foremost, we need to find ways to reduce our energy consumption. So that needs to be by our personal habits, that needs to be by our systems and improvements to our infrastructure, that needs to be through improvements to technology and investment in technology, but we just need to find ways to use less energy than we have been accustomed to in the past. That's number one. And then secondly, we need to find ways to replace the energy sources that we are dependent on. We need to replace these fossil fuels with other energy forming products. And so hopefully this will be done a lot with renewable sources, things like solar and wind energy that can be not used up. And while they all do have some kind of undesirable consequences and costs, these costs are much less in both the short and long term, both economically and socially, than the costs of continuing to use fossil fuels. So we'll talk about some of these alternatives in the next couple slideshows.